It's really just kind of stuck on to the part of the, the number that's the imaginary part. But that's how you add them. To subtract, if I was going to do this in a more rigorous way, first of all, we have to know what the additive identity is. Remember, 5 plus 0 equals 5. 0 is the additive identity. Add it to anything, you get the anything back. That's true with complex numbers too. 0 equals 0 plus 0i. Same thing. Okay? It's a complex number, but it's also a real number. And if you add 3 plus 2i and you add 0 to it, you still get 3 plus 2i. Or if you add 0 plus 0i. So 0 is the additive identity. If I'm going to define subtraction, I really have to talk about an additive inverse or an opposite. Like 6 minus 5 is really 6 plus the opposite of 5, or 6 plus the additive inverse of 5. See, 5 and negative 5 and negative 5 are opposites or additive inverses. When you add them up, you get 0, in other words. Inverses combine to give you the identity. So 5 and negative 5 add up to the additive identity. But to talk about subtraction, if I was going to define it, it's really addition. It's adding the opposite. You'd have to add, the negative of 5. So to talk about subtraction of complex numbers, I really should talk about the additive identity, which is still 0, same thing. And we should talk about the opposite or the additive inverse of a complex number, a plus bi, and the negative of a plus bi, which is just equal. And by the way, again, I'm jumping around here a lot, but when you have complex numbers, the properties that we learned for real numbers still hold true. Like, remember, we've talked about this in class. When you add numbers, addition is commutative. You can add in either order you want. 2 plus 3 is the same as 3 plus 2. That's also true of complex numbers. You can add in any order you want. The associative property of addition is true. You can group things the way you want. 2 plus 3 plus 4. You can add the 2 and the 3 first, then add on the 4, or you can add the 3 and the 4 first. In other words, put grouping symbols around them, and then add the 2. The same is true of complex numbers. If you're adding 3 or more complex numbers together, you can just group them any way you want. You still get the same answer. It's also true that, I'm not talking about multiplication yet, but let me just mention it here. There's a commutative and we have commutative and associative properties for multiplication for real numbers. Commutative property, you can multiply any order you want. Associative properties, you can group it the way you want. That's also true of complex numbers. The distributive property, A times the quantity B plus C equals AB plus AC. We can distribute multiplication over addition. It's also true that you can use the distributive property works with complex numbers. If you have one complex number times the quantity of two others, you can distribute the multiplication, same way. So all those properties hold true. So here, see, if I'm going to define this as these two, these are opposites or additive inverses. These two are opposites or additive, I'll just abbreviate that, inverses, INV, because I'm going kind of long here. Those are additive inverses, just like 5 and negative 5 are additive inverses, but this is imaginary numbers. In the negative quantity A plus B, just because of the distributive property, this is like negative 1 times this. I can multiply negative 1 times each one of those. That's just negative A minus BI, same thing. Okay? So if we subtract two complex numbers, we just add the opposite. Oops. Let me actually do just an example with numbers. We don't have to, I'm not going to do the letters. So let's say we have 3 minus 4i minus negative 1 plus 2i. And let's compare that to 3 minus 4x minus negative 1 plus 2x. Notice I just put an x where the I is. You do it just like this. See, if you were doing this problem, you say, 3 minus 4x. There's a negative in front of this grouping symbol, so it's going to change those signs. You get negative 1, minus a negative 1, that's plus 1. So that negative changes that sign. And it's, because it's like a negative 1 times this quantity, it's minus 2x, that changes that to a minus sign. Negative 4x and minus 2x are negative 6x. Those are like terms, and so are the 3 and the 2. 3 plus 1 is, or 3 and the 1. 3 plus 1 is 4. Whoops, you didn't see all that. But, you just remove the grouping symbol, you get this. If you were adding these polynomials. Then 3 plus 1 is 4. Negative 4x minus 2x is minus 6x. You know how to do that. You can do this the same way. I don't have to say, oh, add the opposite. I can just do it like this. So we have 3 minus 4i minus a negative 1, that's plus 1, minus 2i. Then you have 3 plus 1, that's 4, minus 4 minus 2i's, minus 6i. Just like if that i was an x, a variable. And remember, I is not a variable in this case. It really is a, kind of a special tag we put on this to use these complex numbers. It's like the square root of negative 1, sort of, okay? All right, but that's subtraction. Okay, multiplication. So how do we define multiplication of a couple complex numbers? A plus bi times c plus di. Okay, here's the answer, but don't, you're not going to do it like this, but this is the answer. If I get it right here, let's see, AC minus BD, that's the real part. And then plus, let's see, AD, plus BC, that's imaginary part, I. Now you might say, wow, I got to remember that thing. No, you don't. You don't have to do that. All you do is FOIL it. Watch. Now remember, I squared equals negative 1. All right, so that was right. That's one of the first things I showed you. So if we have A plus BI times C plus DI, since all those properties I talked about with multiplication and addition and all that stuff, with multiplication, how they're, commutative, associative, distributive, all that stuff works, we can just multiply these like two binomials, just like we did when we were working with, polynomials that were binomials. So first times first, A times C. Outsides, these two. I have two plus signs, so A times D times I. Insides, these two. No negative signs, so B times C times I plus B times C times I. Last times last, both positive signs, so B times D times I when I multiply them together. Plus B, D, I times I is I squared. Now remember, I squared is negative 1. So in place of that I squared, I'm going to put a negative 1. So we'll have AC. Okay, let me write it out. I'll write it out a little longer. AD plus ADI plus BCI plus BD times a negative 1. Now remember, I'm putting a negative 1 right there. So that's negative 1 times BD, or minus BD. Hope you see why that's a negative or subtraction of a BD now. Now these two are real numbers. These are imaginary. So let's change the order first of all. So I just have AC minus BD. Let's move it over here. Remember, all those properties of real numbers, the associative and commutative properties of addition, all that kind of stuff, we can do that. Just like if we were, adding a bunch of numbers up, we can do that. And then these two are, like terms sort of, because they both have an I in them. So let's use a distributive property and factor out the I. So we have plus AD plus BC times the I. And then I'll group these two together. Look, AC minus BD plus AD plus BCI. So don't memorize this. FOIL them. For example, suppose you have 2 minus 5i times 3 plus 2i, and I tell you to multiply these out. Multiply or simplify, something like that, if I say that. You're going to FOIL it. First times first, 2 times 3 is 6. Outsides, 2 times 2 is 4, so plus 4i, because they're both plus signs. Inside, see, a negative times a positive, so minus 5 times 3, 15i times the I. Minus 15i. And then last times last, Negative 5i times positive 2i. Negative times positive minus 5 times 2 is 10. I times I squared. But that I squared is a negative 1. So we're going to, let me just remove it right here and put a negative 1 there. Now, you know, don't put some steps in if you show work. But negative 1. Now that's going to change that to a plus 10. So we'll end up with 6 plus 4i minus 15i and then plus 10. So let's add the two real parts together. 6 and 10 add up to 16. And then 4i minus 5i. That's 4 minus 15 i's. What is that? Negative 11i or minus 11i? So it's easy to multiply imaginary numbers. You just got to be careful and use FOIL. And remember, when you get an I squared, it's a negative 1. And, you know, I did it in the right order. When I do them, I usually do first times first, last times last, and then outsides and inside, because that one ends up over here. But, you know, just FOIL it. That's all. Okay? That's multiplication. All right. A word of caution here when we're talking about multiplication. You know, the square root of A times the square root of B, we said, is equal to the square root of AB. But we said that's true when everything's defined. These are not equal if A is less than 0 or A is less than 0, because then we wouldn't be dealing with real numbers. If that's a negative number, A, square root of a negative number, is not real, so you can't use this property. So how would you multiply together? Let's say we had, let's keep it simple, say, what if we had something like this? What would you do? Well, write them in as a in the form with the I, the standard form. So remember, we just learned a couple of minutes ago. Well, I don't know, I threw that paper on the other, but yet when you have something like this, I don't even know if I did any examples, but I'm doing them now. Square root of negative 9. Remember I told you to take the negative out? So square root of negative 9 is just a square root of 9. Take that negative out of there and multiply by an I. So it's that one. Times, same thing for this one. Take the negative out. Square root of 16. And then multiply by an I. Now remember, multiplication is, you know, you still have associative, commutative properties. So, in fact, let's write it like this first. 3i, square root of 9 is 3, times 4i. We can change the order of the multiplication any way we want and group it any way we want. So 3 times 4 is 12. I times I is I squared. I squared is negative 1. 12 times negative 1, negative 12. There's the answer. Okay, so that's how you deal with, if you have square roots of negative numbers, change them into I form and work with that. Okay. Let's see. Okay, we're going to talk about division, but before that, let's talk about what a complex conjugate is. Now, we've dealt with conjugates before, but in fact, we dealt with them in the last video I made, I think, but here's a complex number. Remember, the conjugate, what we do is change the sign in the middle. So A plus BI and A minus BI are complex conjugates. Okay? Let's see what happens when we multiply two complex conjugates together. Let's multiply these. We'll do some number ones too, but I'll multiply this out first. So we just learned how to multiply a minute ago. FOIL it. A times A, first times first. A squared. Outsides. A times negative BI, that's multiply the A and the B together, but it's minus ABI. Insides plus ABI. I'll let you figure that out. I've done enough of this. You should see how that's done. Last times last, positive times negative, minus B times B, B squared, I times I squared. Notice the middle terms cancel out. They add up to 0. I squared is negative 1. So we have a squared minus b squared, but times a negative 1. That's going to change it to a plus sign. We get a squared plus b squared. So notice, when you multiply complex conjugates together, you can FOIL it if you want, but you don't have to from now on. All you do is square the real part, plus you square the imaginary part. This is a real number. There's no I in that. In fact, it's non-negative. That's a non-negative. That's a real number. That's non-negative. You square two numbers. The a and b are real numbers now. There's no i's involved, so they can't be negatives. Even if a was negative 2, negative 2 squared is 4. And this could only be 0 if both a and b are 0. Both a and b would have to be 0 for this to be 0. So it's usually not 0 unless you have 0 plus 0i times 0 minus 0i, which is really 0 times 0. You're not going to get that. This is a positive number, usually. So if you had something like this, those are conjugates. If you want to FOIL it, go ahead. But all you have to do is this. 3 is the real part of both of them. Square it. Plus, pick either imaginary part, the 4 or the negative 4, because you're going to square it. I'll just pick the 4. If it was negative 4, you'd have a negative 4 squared, which is still 16. So you square the 3, square the 4, add them together. That's 9 plus 16, 25. Notice, no I in the problem. Be careful. Remember, this was true. A plus b times a minus b was a squared minus b squared. That's for real numbers. See, there's a minus sign in the middle when a and b are, all real numbers, the a's and the b's. But if there's i's here, you get a plus sign. Look at the difference. Okay? All right. Anyway, those are complex conjugates, and look at the product of them. That's important for what we're about to do. Okay, next let's talk about division of complex numbers. Now, if you have 8 divided by 2, division is really multiplication. It's 8 times the reciprocal or the multiplicative inverse of 2. It's 8 times 1/2. You get 4, obviously, but so and so you have to know what, technically, if I was doing this in a rigorous manner, if I'm dividing by something, I'm going to multiply by the reciprocal or the multiplicative inverse. So I have to know what a multiplicative inverse is. The two numbers are multiplicative inverses if you multiply them together and you get the multiplicative identity. So I also have to know what the multiplicative identity is. 1 is the multiplicative identity. 1 times 5 is 5. 1 times anything is the anything. 1 is also equal to 1 plus 0i. Now, we don't write it like that. Usually we just write it as 1, but it's also a complex number. The multiplicative identity for the complex numbers is the same 1. It's the same thing. It's just 1. I'm not proving that to you or anything, but that's the truth. It's just 1. So if I wanted to find the reciprocal of this, I really want to find another complex number, so when I multiply them together, I get 1. Now that, I could do that. I could write this as c plus di, multiply them out, and then I could do a couple things. I'd end up solving a system of linear equations, but I could do that and prove to you, what it was, but I'm not going to do that. It's just, it would be, too much, just not necessary for what we're going to do. I'm going to show you, I can show you what the inverse looks like, the multiplicative inverse looks like, but I'll just show you how to divide. This is how we divide. So say we had, and I'll explain why it has something to do with this, but suppose you're supposed to perform this division, or you're supposed to express this answer, express, and because we usually do this, by the way, the answers are usually expressed in standard form. Express in standard form, which means I want it to look like this when I'm done, like that. I don't want the I in the denominator. So if I'm going to write it so there's no i's in the denominator, that means I got to get rid of the I out of the denominator. How can you make an I go away? Look what happens when you multiply conjugates. The I disappears. You end up with a real number. So when you multiply complex conjugates together, you don't have an I anymore because you get an I squared in the problem, and that's it. That becomes a -1. So we can use that to help us write this in standard form. In other words, how to divide it and simplify it and put it in this form. So what we're going to do, very, very similar to what we did with rationalizing a denominator when we had two terms down here, like 5 minus 2 times the square root of 3 with a square root down here. Remember what we did? How we changed the sign in the middle and multiplied by 1 and written in a special way? Very similar. So we have 2 plus 3i over 5 minus 2i, and I want to perform this division, write it, in other words, write it in standard form. So I'm going to multiply this thing by 1. But I'm going to write 1 in a special way again, like we did with those other problems. I'm going to use the conjugate of the denominator, which is 5 plus 2i over 5 plus 2i. See, I'm really multiplying by 1, so I haven't changed the value. Now, the denominator is easy. Look, it's 5 minus 2i times 5 plus 2i. Those are conjugates. That's like this problem, or this problem. So the denominator, I know what it's going to be. I can do it in my head. If you want to FOIL those two, you can. But all you're going to get is 5 squared plus 2 squared. Square the real part, square the imaginary part. Doesn't matter whether you use plus or minus 2, because both of them squared would be 4. But the denominator is 25 plus 4. Was that 29? There's a denominator. The numerator is what takes some work. We got to FOIL these two for the numerator. So we end up with first times first, 2 times 5 is 10. Outsides, 2 times 2i plus 4i. Insides, 3i plus 5, or times 5. 3 times 5 is 15, so plus 15i. Last times last, 2 times 3 is 6. I times I is I squared. Remember, the I squared is -1. So we have 10 plus 4i and 15i, that's 19i. And then 6 times -1, that's -6. So we have 10 minus 6, 4, plus 19i, all over 29. You can leave it like that, or technically, if we're going to write it in this a plus b form, a plus bi form, it would be 4 over 29 plus 19 over 29i, with an I off on the side. The real part is 4/29. The imaginary part is 19 over 29. Okay? But don't worry about this. That's good enough. I'm not going to worry about this. But every time you have an I in the denominator, multiply by the conjugate. If you had, some, here, let me get another page here. There's lots of examples, but don't worry about, if you have something like this, say there's just an I there. Remember, that's really 0 plus I. So you would multiply it. I'm going to skip a step here, equals, and then this step. See, the conjugate would be 0 minus I. So you just multiply by -I over -I, for example, with that one. Don't, freak out if there's no real part. Those are conjugates. And then in the numerator, you have 2 times a -I. So you distribute the multiplication. That's -2i, multiplied by that one, plus 3 times a -1. That's -3. Let's just write it as -3. Oops, can you even see what I'm doing? So -I times a 2, that's -2i. And then -1 times 3 times I times I. I squared when I multiply that -I times the 3i over I times -I. Now remember, what you're doing is 0 plus I times 0 minus I. That's still conjugate. So it's 0 squared plus 1 squared. It's really just 1. And you can see that if you write it out. See, if you multiply those together, it's 1i times negative 1i. 1 times negative 1 is negative I squared. Remember, I squared is negative 1. So this is negative negative 1. I guess you can't even see that, but see that if you multiply, if you think of it as 0 plus I times 0 minus I, you can still say real part squared plus imaginary part squared. Just 1. Or if you multiply the I times a negative I, you're going to get negative I squared, which is also 1. But that's a 1 down in the denominator. Then the numerator becomes, this is a negative 1. So that's a negative 1. So negative 3 times negative 1, that makes it a plus 3. So we'll get 3, I'll put it first, put it in standard form, minus 2i over 1, there's the answer. But don't, whatever. If there was a 5 down here, it's already in standard form. If you had 2 plus 3i over 5, that's really the way you want it. Or you could write it like this, plus 3/5 I, 2/5 plus 3/5 I. But don't worry about that. Okay. Anyway, hopefully I beat that to death enough. And let me see, I probably do powers of I. So we did a lot of the stuff. I don't know if I did everything in the book, but I probably did, or most of it. You can look at the book. Make sure you look at the book, the textbook or the ebook, and look at the watch those videos with the book. Like if you I guess you click on the ebook. We're in chapter 9, so you'd click on chapter 9, and then if you wanted problems from 9.9, click on 9.9, and then I think it has a video, maybe in every section. I don't know. I've only watched a couple things from there, but they look okay, and there's other examples. Okay. Now, one last thing here. Let's see. Powers of I. That's the last thing. So let's talk about that. You should be able to raise I to any integer power. Powers of I. So we have I. Now watch this pattern. So I, we just, it's just I. Kind of silly, but I. If I square it, I squared we said is negative 1. And let me go over here a little farther so I got more room. So we have I squared is negative 1. Let's look at I cubed. I cubed is I squared times I. I squared is negative 1. That's negative 1 times I. That's negative I. I'm just going to write it here so they line up. Whoops. This is negative I. Everybody see why? Because the I squared is negative 1. I to the 4th power is I squared times I squared, or you could think of it as I squared squared. But I squared is, look, is negative 1. So you really get negative 1 squared. See, I'll put it over here. Negative 1 squared, which is 1. So I to the 4th power is 1. Oh, look, I, negative 1, negative I, 1. Now watch what happens if I start raising it. Here's first power of I, second power of I is negative 1, third power is negative I, fourth power 4, or 1. So now I'm going to go I to the 5th power. And I'm always going to use I to the 4th now once I'm above 4. These are nice positive integer powers. That's all you have to do. Can you raise I to the 1/2 power? Yeah, you can take the square root of I, but we can't do it. You even need trigonometry to do that. But I to the 5th, I'm going to write as I to the 4th times I. I to the 4th is 1, so that's 1 times I. I'm right back to I. See, I got these 4. Okay, now watch. I to the 5th, I get I again. I to the 6th is I to the 4th times I squared. I to the 4th is 1. This is 1. I squared is negative 1. So we get 1 times negative 1. Negative 1. Notice I got an I again. I got a negative 1 again. I to the 7th power. I always use somehow I use I to the 4th. I to the 4th times I cubed. That's what I to the 7th is. I to the 4th is 1. I cubed, look, negative I. I get negative I again. Okay. I to the 8th. That's I to the 4th squared. That's 1 squared. 1, 1. So look, the pattern is I, negative 1, negative I, 1, I, negative 1, negative I, 1, over and over and over again. But if I said, what's, I to the 36th power, in fact, let's just keep it kind of even simpler. Let's say, well, that's fine. Well, I to the 40th, let's say. If I say that, I don't want you to, figure out I to the first, second, third, fourth, all the way up to 40. Every time you have an exponent, you got to know these first four. If you have an exponent bigger than 4, you can do this. See, I can write this. First of all, 4 goes into this. So if the exponent is bigger than 4, I want the largest number that's a multiple of 4, that's less than or equal to 40. 40 is a multiple of 4. That means I can write it like this. I to the 4th to the 10th, because 4 times 10 is 40. I to the 4th is 1. 1 to any power is 1. So every time this exponent is divisible by 4, you get 1. I to the 41st power. 41 is not a multiple of 4. So I want the largest number that's less than or equal to 41 that's a multiple of 4. 40. So I'll write this as I to the 40th times I to the first power. I to the 40th is this. If 4 goes into this exponent, it's 1. So this is 1 times I. I get I. Notice if I divide 4 into 41, my remainder is 1. That's the exponent on I. Let's do I to the 42nd power. 42 is not a multiple of 4. The largest number that is less than or equal to 42 that is a multiple of 4 is 40. So I could write this as I to the 40th times I to the second, because I would add those exponents. Since 4 goes into 40, this is I to the 4th to the 10th. That's 1 to the 10th power. That's 1. So I just get I squared, which we know is negative 1. In other words, if I divide 4 into 42, the remainder is 2. So I just put 2 on as an exponent. I squared is negative 1. I to the 43rd, for the same kind of reason, I can write as I to the 40th, which, 40 is the largest multiple of 4, less than or equal to 43, times I cubed. I to the 40th, just like we've been saying, is 1. Times I cubed. I cubed, you're supposed to know, is negative I. Just know those first 4. But again, you could just divide 4 into 43. Remainder's 3, so it's I cubed, which is negative I. So whatever I give you, you should be able to do it. If I gave you I to the 102nd power, say you just did it by dividing by 4. If you divide 4 into 102, let's see, 2 4s are 8. Bring down the 2. Subtract it to 2, bring down to 2. 4 goes into 22 5 times. 5 times 4 is 20. Remainder 2. This is I squared, which is negative 1.